So the plan for this session is just to get you ready for the exam, or make sure you're ready for the exam. Um, I'm not going to work out many of these problems, or any of them at all, actually. The idea is just to lead you with some good questions, because you guys should know how to do all these. So I'm going to add a link to the questions to do yourselves, but ideally you know how to do all these questions. I can just show you that you do know how to do all these questions. So that's it. So the first problem we're going to review is the air plug problem. We've got, of course, mass 1 is 0.16 kilograms tied to a string. Revolves in a circle of radius 1.2 meters. And we also know that the mass suspended below the table is 1.8 kilograms. So 0.8. We want to find first the tension and second the speed or velocity. So of course I always start by deciding what we're given and deciding what we need to find. So of course here we've got the masses and the radius given, and we want to find the tension and the velocity. So yeah, one string, one tension. This isn't overly tough. First question I wanted to lead you with was, what type of problems have we seen before with similar elements? If you think about that, you'll sort of think that we've looked at Atwood's machine problems that were sort of similar. Very similar, actually. So very similar in approach. You're going to look at one mass separately from the other, do a free body diagram of both. That's your process. Two, what laws or equations will you use? Here, it's pretty straightforward. I basically already told you, but you would use Newton's second law. So that's just sum of the forces equals mass times acceleration. And that's not overly difficult. You also want to know what forces act on the second or the hanging body, and that's where you differentiate. So that sort of builds on the first two questions. What forces act on the second or the hanging body? Let's actually draw a diagram for that. So you've got one force going up and you've got one force going down. So what you think about that, but you should have tension going up and weight going down. Those are your two forces acting on the hanging body. Next, they ask you what forces act on the first body. So that's really the question. What forces act on the revolving body? It shouldn't be overly difficult. Maybe I should specify that we're looking at the rotating dimension. So that would just be one force, and that would be, let's draw it, tension in the string. So tension. I drew that. Maybe that's a bad picture, but the idea is tension is causing the centripetal force, centripetal acceleration, and that was the fifth question. So not overly difficult. You should be able to work that out yourself. The answer I've gotten for that is 17.64 newtons, and for B, the speed or velocity, I've gotten 11.5 meters per second. So let's see. So next question, we've got the roller coaster question. We've got a vehicle of 600 kilograms, mass 600 kilograms. And point A, we're going to say that the speed is 18 meters per second. So velocity at point A, 18 meters per second. And point B, we're going to say, actually, what is the maximum speed the vehicle can have at point B in order for gravity to hold on the track? So we want to know the speed at point B. So that's what we're looking for. Pretty clear. Mass 600 kilograms. We've got A's velocity, we don't have B velocity. We're looking for the normal force in part A, correct? So I didn't write that. Okay. So the questions I've I want to ask you guys what laws or equations will you use, and that's not overly difficult at all. Here you're going to use Newton's second law again. So sum of the forces equals the mass times acceleration. One thing to consider though is this isn't your typical acceleration, is it? You're going to have to use centripetal acceleration. So it's going to be the fancy A, and that'll either be v squared over r or omega squared times r. So one of those. So you've got that. What forces act on the vehicle at point A? You can actually draw it. So you should have on your diagram one force going up, one force going down, right? It's not overly difficult. One force going up, a weight going down, right? Ask what forces act on the vehicle at point B, and it should be the exact same thing. So, normal force going up, weight going down. And lastly, I want to see if you guys knew what is the normal force of the track on the vehicle. The vehicle is off the ground. And that's sort of a trick question. If it's off the ground, there's no way there could be a normal force. So there's going to be zero normal force there. So not too difficult. Let's just skip to part B actually, because a little bit trickier. Let's draw it. Not exactly tricky, but if you're not familiar with the concept, it could be easily missed. That's 15 for the radius. We've got, of course, normal force going up, weight going down. So we're drawing this, and take the time to write out your Newton's second law equation. So see what you get. And by now you should have something, and I've got some of the forces to equal negative mv squared over r. So the idea here is that because we have centripetal acceleration, and centripetal acceleration always points towards the center of the circle, we're at the peak of the circle, so the centripetal acceleration is going to be pointing down in your negative direction. So that's one thing to keep track of, but otherwise this problem is not overly difficult. So here's another good one. We want to know, or we want to calculate rather, the net torque on the beam in the figure below about the c-axis. So net torque here is just essentially the sum of the torques. So I just want to figure out the sum of the torques on the beam in the figure below about the c-axis, and if you can't see very well, the c-axis is that axis rather in the center of the beam. So that's what we're looking at. First leading question I wanted you guys to think about was, how would this beam rotate? So I actually made a little demonstration. You've got the beam essentially, this is your c-axis right here, it's going to rotate like this. This is how your beam would rotate if you were looking at it from the front, as in your diagram. So that's the idea. Next, I want to know, how could we apply forces to this beam to make it rotate? So say we added a force, straight up, right? That would go, it looks, this is clockwise for me, but maybe different for you. And similarly, on this side you press up, it's going to go counterclockwise. So definitely want to consider how your body is going to rotate, how it's going to work about that axis, because it could be different for any body. So we did that. Which way is positive? So here, or actually in any situation, we say that counterclockwise is the positive direction and clockwise is the negative direction. You guys should know that. Next, I want you guys to see what laws or equations we will use for this problem. So that's just like my standard question, probably going to be something you look at for everyone. Make sure you know what you're using. But what laws or equations will you use for this problem? So not overly difficult. You just want the torque equation. So torque, you just want torque equals radius times force times sine theta, right? And you should know that one like the back of your hand at this point, because you will be using it a lot, or you should have been using it a lot. So torque is radius times force times sine of theta. And think about this, what angle are we focusing on when we use theta? What exact angle? Next question I want you guys to look at was, will the 49 Newton force create positive or negative torque? So you see the 49 Newton force is going down and to the body's right. So how would that affect the body? And then similarly for 6, will the 10 Newton force create positive or negative torque? And you'll see that they're going to make the beam rotate in different directions, right? So you shouldn't get the same answer for that question. And that is it. So next question is the arm question. We've got the arm, and it weighs 40 newtons. The force of gravity is going to be pulling on the arm through point A, which is right there in the center, which is 0.290 meters from the shoulder. Force T is what we're looking for. We're also looking for force S, and that is it. So we have weight acting at the radius 0.29 meters. 0.29. We're looking for force T, and that is 0.08 meters away from the origin, or yeah, the origin, 0.0. And we also have force S, which is at 0.0. And you want to see exactly what that force is, and we don't know the angle. We don't need an angle at this point. So let's see. Write out what you have and what you need, and that's always our first step. So here's all right. So from left to right, this is what we have. Got the weight, which is 0.29 meters away from the 0.0. We're looking for force T, and we know that it is 0.08 meters away from 0.0, and we're looking for force S as well, and then it's exactly on 0.0. So that's what we have. That's what we're looking for as well. First question is going to be, what laws or equations will we use for this problem? So twofold here. Think about it for a second. And similar to a few we've done previously. Of course, we're going to use the torque equation, right? So write that out. And I'm not sure if you've noticed just yet, but we're going to use Newton's second law as well, right? So Newton's second law, we know that. And if we have an arm hanging in equilibrium, right? There's no torque, and there is no, there are forces acting, but there's no motion, right? So we could say that some of the torques is going to equal 0, right? We could say that some of the forces is going to equal 0 because there's no acceleration or movement. So that is what we have to start, right? what would you decide is the axis in order to solve the problem? I may have sort of given it away if you think about it for a second, but we're going to say that point O is the axis. So point O right here at the inside of the shoulder is what we're going to say is our hinge, and if you look at your actual shoulder, that makes a lot of sense. So any forces that act like right here aren't really going to do anything. Got that. So we want to know what the torque created by the force T be positive or negative. And this points back to what we did with other questions, I think maybe 3. Be positive or negative, and it depends on the hinge, how it acts, or how it makes the arm react with the hinge. So force T, right? We've got it going essentially up and to the medial area. So it looks like it's going to make it go, based on my picture, counterclockwise. So it's going to be a positive force. And we see that the next question wants to know about the weight. Opposite, so it's going to be negative, right? And then last question, we want to know if we determine that that to the right and upper positive is force T in the positive or negative direction, negative Y direction. So consider that, and also consider if it's in the positive or negative X direction as well. And that's essentially the key to solving that problem. Alright, we've got for number 5 a solid uniform disc of radius 0.360 meters. So we've got a disc, and it's got a radius of 0.360 meters. So let's write that. And we've got a mass of 64 kilograms. So mass for that disc can be 64 kilograms. Rolls down a ramp of length 4.8 meters. So the ramp length, let's say, is 4.8 meters. And it makes an angle of 24 degrees with the horizontal. So right now, I'll just write out what we know. So take some time to do that. And we also know that this starts from rest at the top of the ramp. So it starts at rest at the top of the ramp. So let's actually draw this as well, because I think that will give you a good idea of what you need to do here. But first of all, what we have is this, and we also want to find the speed, and we actually want to find the speed of the center of mass and the speed, and the angular speed rather, of a disk. So 2 different speeds. So write that. I'll just write the variables, and that should give you a hint to what we're exactly looking for. So everything we have and know, and the 2 variables we're looking for. So let's draw this. We've got a ramp, we've got a disc, which would be another hint to what we're going to be doing. Disc, let's just say. Let's fill it in. Throughout the ramp of the disc, we've got a length of 4.8 meters. Let's draw that. Angle is 24 degrees from the horizontal. And that is that. So here is my picture. The ramp, the disc at the top, 24 degree angle. And that is what we're dealing with. My leading questions are, what type of problem is this based on those we've seen in the past? So consider that for a second. And if you said it is a conservation of energy problem, you're exactly right. We're going to just do conservation of energy. So we've got that. Number two, what laws or equations will we use for this problem? So, pretty simple, conservation of energy formula. Kinetic energy initial plus potential energy initial should equal what? And it should equal the exact same thing. So we're going to say conservation or kinetic energy final plus potential energy final. So yeah. The idea though is that we have translational kinetic energy. We have what's the word? Rotational potential energy or kinetic energy as well. So we're going to write both of those: translational kinetic energy, which is what we're used to using, and rotational kinetic energy. I may have misspoken. Kinetic energy plus we're just writing out our formula with the new things, new variables. And here's what we have. Initial and final, we've got the kinetic energy that we're normally using right here. And we've got the rotational kinetic energy, which we are applying now. So let's actually stay here. At the top of the ramp, we're going to have kinetic energy or potential energy at rest. And you should know that if we're at rest at the top of the ramp, we're going to have only potential energy. We're at a height above the ground, and we are not moving, so only potential energy. As the disk rolls down, right, we're going to have kinetic energy, right? So we have kinetic energy translationally and rotational kinetic energy as well. So here's what I've written, and that's what we're going to focus on. And the idea there is that we're normally using translational kinetic energy. So imagine we have the ramp and it just slides down, no rotation. But in real life, right, we're going to rotate a little bit. So different, very different. So we're going to have both. So what is part A asking for? And that is asking for the translational kinetic energy. So pretty straightforward. Part B is asking for the rotational kinetic energy or the speed, but that's the idea. We're going to focus on those ideas. Number 4, what is the relationship between tangential and angular velocity? That should be on your formula sheet. It should be tangential velocity equals angular velocity times the radius. So if you know that, you're good. Let's write that out. Tangential velocity equals rotational velocity times radius, or angular velocity. What is radius? So not overly difficult. And then lastly, for part 5, or question 5, I want to know what advice have you been given for these type of problems. So I've told you, I'm sure Daniel's told you, Espino's definitely told you, that you want to stick to the variables and simplify as much as you can before you do any math or plugging in. It's so much easier that way. So I'm actually going to start this one up for you. So initially we have potential energy, and beyond that we've got translational kinetic energy and rotational kinetic energy. So take the time to write that out. Write out your formula or equation. And you should get something like this, right? That's not all though. So you want to find the translational kinetic energy or translational velocity initially. So we're going to change inertia to a bit simpler terms, right? Simplify that. We're also going to change omega to use tangential velocity terms. So let's take the time to do that. You should have no problem doing that. And remember, we are using a disk, so we're going to have a special moment of inertia formula for a disk, right? So plug that in there. And then, of course, change the omega to velocity terms. So if you're finished, you should have, let's erase a little bit. You should have this, right? Of course, that is not completely simplified, so we're going to simplify even further, right? All the masses cancel out, so we can erase the masses. 1/2 times 1/2 is 1/4, of course. R squared times b squared over r squared is just going to be the v squared, so I'm looking at this right here. R squared times v squared over r squared, we're going to cancel out both those r squares. So now we've got GH equals 1/2 b squared plus 1/4 v squared, right? So 1/2 plus 1/4 is 3/4. So we've got GH equals 3/4 v squared. And if that's the case, the square root of 4/3 GH should give us our velocity. And from there, you can just plug in. Let's get that in there. From there, you can just plug in, but yes, gonna give you some wonky numbers if you try to do it the longer way. Maybe it's not longer, but a bit messier. So try to simplify as much as you can before you do any math. And that is the idea there. So for 6, we've got a ball with radius 0.0225. So radius is 0.0225 meters. Average density is 75 kilograms per cubic meter. So got that. And that should be on your formula sheet as far as the variable. You want to know what force is required to hold a completely submerged underwater. So, of course, you're taking your time to write out what you know and what you're looking for. And that is that. And of course, there's more on your formula sheet. You'll see you have a lot of it on this problem. So my leading questions were, what laws or equations will you use for this problem? And let's actually draw this. Let's draw this one. So we've got a body of water. Let's say it's got our object being submerged in the water. And I'll show you that, just what I've drawn so far. So maybe that'll give you a hint as to what laws or equations we'll use. But if you're not come up with anything, we're going to be using Newton's second law again. So you know what that is. Sum of the forces equals mass times acceleration. So you can write that out. But we've got our body in the water. We've got forces acting on it. And take the time to draw your forces on your diagram. And we can sort of meet together. So we've got one force going up. We've got two forces going down, right? One force up, two forces down. So that, and we've got Here's what I've drawn. Let's see if you have anything similar. We've got the body, or we've got the body of water, we've got the object inside of it, we've got force and the weight of the object going down, and we've got the weight of the water displaced going up, or the buoyant force. So buoyant force is just the force provided by the weight of the water displaced. So that's not overly difficult, you should know that. And it's also on your formula sheet if you didn't know it. You can sort of discern it if you needed to at the last minute. So we've got all that. So yeah, that's all the information we need there. We use Newton's second law. What is the acceleration in this scenario? And I sort of gave it away actually. We're going to assume that the entire system is held in equilibrium. We've just got the object being held underwater. So the buoyant force is pushing back up, but the force and the weight of the object are counteracting it. So you're sitting down there in equilibrium underwater. Last question is going to be, where does the radius come into play? So that's a good question. That's a really good question. So you're going to work it out to find the force, right? You're going to use your Newton's second law, and you're going to say that the force should equal the buoyant force minus the weight of the object. So this is what we have so far. You know that the density of water is 1,000 kilograms per cubic meter. Move that to the side a little bit. Density of water. We know that gravity is 9.8, but we don't exactly know the volume just yet, right? We can figure it out. We've got the radius, and we'd use the radius to figure out the volume, because the volume of water displaced is going to be the volume of the object. So we've got all that. And I think the main idea beyond that is, how do we use the radius to get the volume of the object and of the displaced water? And that would be volume of a sphere, which is 4/3 pi r cubed. So that's where the radius is going to come into place. You're going to use your radius there, plug it in, whatever you get for the volume and the buoyant force and the weight. So not overly difficult there, and you should have no trouble with that problem. Alright, now we're going to look at the gravitational force exerted on a solid object is 8 newtons as measured when the object is suspended from a spring scale. So we've got a spring scale holding the object and measuring its weight. When the suspended object is submerged in water, the scale reads 4.28 newtons. You want to find the density of the object. So take your time to write out what we're given and what we want to find, right? So hanging 8 newtons, submerged, we're reading 4.28 newtons. And we want to find the density. So everything we've been told is right there. Leading questions are, what laws or equations will you use for this problem? That's not difficult. We look at your figure. You see a free body diagram. Anytime I see a free body diagram, I assume we want to use Newton's second law. So we know that sum of the forces equals mass times acceleration. And here, right, we've got a spring scale holding on to the object, If that's the case, no movement here, right? So acceleration is 0, sum of forces should equal 0. So we've got that. We want to know, what does the 8 Newton measurement represent, right? So let's draw it. We've got our spring scale, the object connected to the bottom, and it's just suspended in air, right? So here is my little picture, and you want to add your free body diagram to that, right? So free body diagram, we've got force going up, and we've got force going down, right? Your two forces should be tension and weight, and that is our free body diagram. So the force that your spring scale is reading is the tension. Tension here reads the weight. That's all it reads, right? So the weight here is going to be 8 newtons, just like the tension. So the tension is 8 newtons, the weight is 8 newtons. That is the case right here. And that's just simple Newton's second law. Tension should equal the weight. So we've got that. The 8 Newton measurement is the weight. We also want to know, what does the 4.28 Newton measurement represent? So let's draw that scenario. We've got the object submerged in water now. So draw that. So here is my new picture. Same thing, but the object's now in water. Free body diagram. We of course have the weight going down. We have two forces going up now, right? Anytime we have an object in a fluid, displacing that fluid, we have what force acting on it, going up? And that would be the buoyant force. So buoyant force on our free body diagram, we can write tension and we can write weight, right? So here's my new free body diagram. Buoyant force going up, tension going up, and weight going down. So I already told you that our actual weight is 8 newtons, right? And I also told you that the reading from your spring scale is going to be the 4.28 newtons. Or that's what I'm telling you, is that the reading from your spring scale is going to be your tension. So you'll see that the buoyant force and the tension should counteract the weight, right? So if we do 8 minus 4.28, we can get our buoyant force. So 8 minus 4.28 will give us our buoyant force, which is 3.72 newtons. I didn't write newtons, but you know that it would be in newtons. So what I was getting at for my leading question part, or in question 3, was that the 4.28 represents the weight being offset by your buoyant force. So it's your weight represented, or it's your weight being offset by the buoyant force there. So we know all that. We can erase a little bit. And those are the only questions there. This problem isn't overly difficult. The main idea there is, of course, to understand what you're doing with your free body diagrams, and also you want to understand your relationship between the buoyant force and your weight of the object, or the buoyant force and the actual object, right? So the amount, or the volume rather, of the object that displaces the water should be equal to the amount of water displaced. I may have said that sort of weird, but the idea is, if you drop, say, a 4 kilogram per meter cubed object in a bucket of water, you're going to have a displacement of 4 kilograms per meter cubed. So that's the main idea. Not too difficult, but you guys should know all that, and that's it. Alright, so this one we've got water moving through a restricted pipe in a steady ideal flow. At the lower point, in the figure below, which is 0.1, we're going to say that the pressure is 1.88 times 10 to the 5th Pascal. So you write that out. Pressure at 0.1 is 1.88 times 10 to the 5th Pascals. Pipe is radius 0.028 meters at 0.1 as well. So radius 1 is 0.028 meters. At the higher point, actually, we've got, of course, our height is 2.8 meters. So our height up is 2.8 meters. Write that down. Pressure there is 1.44 times 10 to the 5th Pascals. So pressure 2, 1.44 times 10 to the 5th Pascals. And the pipe radius at that point is 0.018 meters. 0.018 meters. So we've got all that, and we want to find the speed of flow in the higher section, so that's velocity 2. So far I've just written out everything we know. Always write out what you know, it helps you. Leading questions are, what laws or equations will you use for this problem? You're going to use Bernoulli's equation if you didn't know. So Bernoulli's equation, that's in our formula sheet. You've got pressure 1 plus 1/2 rho velocity 1 squared plus rho gravity height. The rho we know is density equals pressure 2, but with the 1/2 rho velocity 2 squared and rho or density times gravity times height. So let's see. Here's what we've got, and it looks really similar to conservation of energy. Like Espino pointed out, it looks similar. It's essentially conservation of energy with fluid. So actually, don't quote me on that. Don't quote that, because it's not conservation of energy necessarily, but it's conservation of pressure. How about that? Conservation of pressure. So we've got all of this. You want to plug in our values, of course. You want to make sure you've got your size separated. But this isn't too tough. This isn't too tough at all. We also want to know what is the relationship between the velocities of both openings. So here I'm looking for you guys to find like the equation, the physical formulaic relationship, because you'll start to solve your problem and you realize you don't have velocity 1 or velocity 2, and you can't solve the problem with only one equation. If it has 2 missing variables, you have to have 2 equations at that point. So 2 missing variables, 2 equations. Your second equation is going to be what? And it should be your continuity condition. So that's going to be A1 V1 equals A2 V2. So area 1 times velocity 1 equals area 2 times velocity 2. And we're looking for the speed at the higher section, so we're going to make this in terms of, we're going to solve for V1 and make the larger equation in terms of V2. So how we demonstrate that, we're going to make A2 over V2, or A2 over A1 times V2 should give you velocity 1. Let's clarify that. So here's that. Just moved area 1 to the side by dividing. We have our numbers. We can plug in the area. We don't have the exact areas, but we can find them out. Area, or cross-sectional area, is going to be pi r squared. We've got our radiuses. So we're going to do pi radius 2 squared. Radius 2 was the 0.018. And then area 1 will be pi times. Boy, what's up, man? Yeah, I feel you. We're going to do pi times 0.028 squared. And that's it. So, not too tough.
So really good stuff there. Really good concepts. I think if you could do all those questions and you understood all those concepts, and you'd be good for the exam. Of course, we didn't touch everything, but those are some good overarching things. I'm going to touch more in my next session. Maybe a few more with the Bernoulli's equation, maybe a few more from Chapter 8. But not too tough. I think once you guys get those exact concepts down and a few more, get a lot of practicing, you should be good for your exam. But otherwise, I think you guys are essentially ready. Feel free to leave any comments, leave any discussion posts you want, email me, email Daniel, email Espino, of course. But that's it. Thanks for watching.